In this video, we'll be solving question number 55 from GATE Chemistry 2019 paper. So the question is the following. Consider a two-dimensional harmonic oscillator with angular frequency omega x equal to 2 omega y equal to 6.5 times 10 to the power 14 rad per second. And the wavelength of X polarized light required for the excitation of a particle from its ground state to next allowed state is. So round it up to first decimal to 1 decimal place. So here we have to find out the wavelength of X polarized light. Here X polarized light is important because it only excites the harmonic oscillator states of the harmonic oscillator along X direction. So from ground state to next allowed state. Okay, so let's find out. So first let's recapitulate the basics of simple harmonic oscillator. So we know the simple harmonic oscillator, or in short SHO, is follow the Hooke's law. That means force is proportional to displacement. Here F is the force and x minus xc is the displacement from the equilibrium position. Here xc is the equilibrium position. Here the minus sign is very important because it actually tells us that it is a kind of restoring force. That means if you go further away from the equilibrium position, then the force will be higher and it will pull you back to the equilibrium position. Now after inequality, so F will be equal to just minus k times x minus xc, where k is the force constant. So from this equation we know that for conservative system force is minus dvx by dx, where v is the potential energy function. So minus dvx by dx equal to minus k times x minus xc, and from this equation we can write down the expression of potential energy function, which is vx equal to minus half of k x minus xc square, where omega is the angular frequency of the harmonic oscillator, omega equal to root over of k over m. K is the force constant, m is the mass of the oscillator. So Vx will be equal to, if you substitute k here, half m omega square x minus xc square. Okay, now some quantum mechanics of harmonic oscillator in 1D. So if we solve the quantum mechanical problem of 1D simple harmonic oscillator, we get the energy eigenvalue En equal to n plus half times h bar omega, where En is the nth energy for the n corresponding to the nth quantum number. Here n is the quantum number. For harmonic oscillator, the allowed values of n is 0, 1, 2, 3, etc. H bar is the h over 2 pi. H is the Planck constant and omega is the angular frequency. Now for harmonic oscillator, the allowed transition is, condition for the allowed transition is delta n equal to plus minus of 1. Now let's say for 0 to 1 transition, here in this case delta n equal to plus 1, so it is allowed. But from 0 to 2 transition, delta n will be equal to plus 2, so it is the forbidden transition. So the condition for allowed transition is delta n will be equal to plus minus of 1. So like 0 to 1 transition, 1 to 2 transition, 2 to 3 transition, these are allowed, but 0 to 2, 0 to 3, 1 to 3, these transition are not allowed, so it is forbidden transition. Okay. Now for a 2D harmonic oscillator, that means there is one harmonic oscillator along x direction and there is another harmonic oscillator in y direction. These two are independent, not interacting with each other. For this case, the energy eigenvalue will be the summation of both harmonic oscillator, energy eigenvalue for both harmonic oscillator. So E is a function of nx, ny. That means for nx is the quantum number corresponding to the harmonic oscillator along x direction, and ny is the quantum number corresponding to the harmonic oscillator along y direction. So in E nx ny will be equal to nx plus half h bar omega x plus ny plus half h bar omega y. Here omega x is the angular frequency of the harmonic oscillator along x direction, and omega y is the angular frequency of the harmonic oscillator along y direction. Now so in this question we are using X polarized light. That means it will only excite the harmonic states of the harmonic oscillator along X direction. The Y direction will not be disturbed. Now for ground state, now in the question it is asked from ground state to next allowed state. So ground state means Nx equal to 0, and next allowed state means delta n has to be equal to plus minus 1. So next allowed state for this case will be equal to Nx equal to plus 1. So for this transition, for Nx equal to 0 to 1 transition, delta E, change in energy, will be equal to E of 1 comma ny. Ny is fixed here. Let's say the quantum number corresponding to the harmonic oscillator along y direction is ny. So ny will not be disturbed here. So for this transition, delta E will be equal to E1 comma ny minus E0 comma ny. So now let's put all these values E1 comma ny and E0 comma ny. So 3 by 2 h per omega x plus ny plus half h per omega y minus half of h per omega x plus ny plus half h per omega y. Now this term, the two term will cancel each other. So the delta E for this transition will be equal to just h per omega x. Now so omega x value is given here. So omega x equal to 2 omega y, which is 6.5 in times 10 to the power 14 rad per second. Now let's just focus on this part. H per omega x, that means h bar means h over 2 pi times omega x. Again the delta E, that means change in energy due to transition, we can write down is equal to h per omega x, or it is equal to h nu, where nu is the frequency and omega x is the angular frequency. So we can also write down nu equal to c over lambda. C is the speed of light, lambda is the wavelength. So in short we can write down h by 2 pi omega x equal to hc by lambda. H will cancel out each other. So lambda will be equal to 2 pi c divided by omega x. Now we know the value of c, we know the value of omega x, so let's put all these values and we can get lambda equal to 2.898 times 10 to the power 6 meter. Now if we round it up to 1 decimal place, that means it will be equal to 2.9. Oh sorry, it will be equal to 3. So the wavelength of the X polarized light is 3 times 10 to the power minus 6 meter. Now for further details you can visit the following NPTEL reference, which is the NPTEL lecture series on the topic of quantum chemistry of atoms and molecules. Instructor is Professor Anindya Datta from IIT Mumbai. Thank you.